Hello, this is Kevin Buzzard going through the solutions to 2019 University of Edinburgh example sheet question about finite dimensional vector spaces. And what does it say? It says that if I've got a 9-dimensional vector space, so what are the variables? So K is a field, V is a vector space over K. Note that we call that modular KV. That should be fixed really, but still. If A and B are subspaces of this 9-dimensional of this space V, and if V is 9-dimensional and the subspaces are both finite dimensional, then the claim is that their intersection can't be the zero space, and this is the bottom of the lattice of subspaces. So I talk about this up here. This bot it's the smallest subspace. And so it's the zero-dimensional. It's not the empty set, right? It's the zero-dimensional subspace. Obviously, the intersection of two vector spaces can't be empty because it contains the zero vector. But we've got to prove it contains a non-zero vector as well. And I mean, to prove this, the key thing that one needs is this submodule dim sub and dim inf ec. So let's see what that says. Have H is going to be defined to be, let's put that first. You see, H is asking as input, H wants as input two submodules, so this would be A and B. So H says that the dimension, fin rank is dimension. The reason you don't want to use the normal dimension, I mean, this is a bit technical, but the reason you don't want to use, maybe I should even try this, check, what's it called, dimension or, it probably just said it. It's called module.rank. Module.rank V. Let's see what we get. You see, the problem is it's a cardinal, which is it's probably module rank KV. Yeah, there it is. It's a cardinal, which is some kind of generalization of a number. I mean, the idea is it's going to be very inconvenient if we have lots of different kinds of infinity in this calculation. We'd rather work in the natural numbers. So the rank of an arbitrary vector space can be infinity. So this function returns what's called a cardinal. But we use fin rank instead, which only works for finite dimensional vector spaces, and gives a natural number. That's the point. So this statement says that the dimension of A plus B at the dimension of A intersect B is equal to the dimension of A at the dimension of B. This is some standard result in the theory of vector spaces, and the proof is lots of sort of Steinitz exchange lemma faffing around. You write down a basis for A intersect B, you extend it to a basis for A and extend it to a basis for B, and then you prove that the number of things you've added is, that's what then you do the calculation. So that's the key thing. And of course we know, what do we know? We know the dimension of A and we know the dimension of B, so we can rewrite HA and HB as H. So now we know the dimension. So we're trying to, obviously we're trying to say something about this A intersect B. We're trying to prove it's not zero. So basically we want to prove that it's not zero dimensional. So we need to get a contradiction. If A intersect B were zero dimensional, then this number would be 0, and this number would be 10. So this number would have to be 10. The dimension of A direct sum B, the subspace of V generated by A and B, would have to be 10, but it's bounded above by 9. So that's another thing we're going to need, right? We're going to need have H1 is the fin rank of A join B, or of A sub B. Is at most 9. Fin rank V, and it doesn't. Why does it not like that? Oh, it doesn't know that this is a subspace. So let me tell it it's a subspace. And it's not called subspace anymore. Sorry. No, it is called subspace. I've just forgotten the field. Subspace KV. There we go. Is the most fin rank KV. You've got to put the field in always. Because of course a complex vector space is also a vector space over the reals, but the dimension doubles. And library search should do that. Although actually I did this already. What's it called? It's called, oh, it didn't do it, rotten luck. It's called submodule finrank LE apparently. So this would be submodule finrank LE A sub B. And what have I done? Oh, that's odd. Maybe I should just stop trying to claim what I think it says and just say this. Let's let H1 be that. Oh no. Yeah, that looks fine. I don't know what I was doing wrong. Well, so there you go. And so we know that the rank of A plus B is at most the rank of V. So we better rewrite HV at H1. So now this is at most 9. And I guess we're going to prove this by contradiction. So we could sort of intro H2. A intersect B is bot. And then have H3 can say that the dimension or the fin rank of A inf B as a submodule of V is 0. And I'm hoping that if I just rewrite H2, now this says the fin rank of bot is 0, and library search will find it, although it's down, it's fit. I mean, I don't need to do library search. What is the theorem about fin rank of bot going to be called? It's going to be called fin rank bot, right? There it is. Oh, hard luck. Fin rank bot, do I need to feed it? I'll tell it K. Will that make you happy? No. So maybe it's just exact this. How about that? Oh, what have I done? Oh, fin rank bot. Oh no, I still need a V. I need a V? Oh yeah. Oh dear. What's going on? Oh, I see. Oh, I'm a fool. This is a K. There we go. I bet this would all have worked now. Apply fin rank bot. Let's see how many times in this lecture I forget to say the field we're working over, and I guess it is kind of important. So now we know that this fin rank of the intersection is 0, so I can rewrite H3 at H. And so now, right. So now this says that this is at most 9, and if I add 0 to it, I get 10. I think we might be at the point where Linarith can do it. Yes, there we go. And so that's the end of this video. Thanks very much for watching.